highest fraction.
Oh, really?
So, I mean, it's not in their interest,
I assume, yeah.
but it is in their interest to let me.
All right, we should get started. Mark is in Stanford, so I'm kicking things off today. Super happy to have Jim talking to us about flow information approach to granular IV. So
Thank you. Thanks everybody for coming. This is joint work with Christiana Baumeister at Notre Dame. And there's a lot of information to be obtained comparing what happens locally with what happens in the aggregate, information that can help identify structural magnitudes. An example of that everybody's familiar with is Bardic type instruments, where we can use a weighted average of aggregate conditions where the weights are given by local shares and use that potentially as an instrument to estimate what happens at the local level. Recently, there's been some interest in this idea of granular instrumental variables, which is a claim that in some situations, you can use the difference between a volume weighted average of what everybody's consuming and an arithmetic average of what everybody's consuming. Use that difference as a potential instrument to estimate elasticities of producers. If you haven't seen that idea of granular instrumental variables, I'll be presenting a motivation for it. I'll give an example of how that could arise as something that you could use for identification. And in the context of looking at that example, I'll point out that in fact, it's a very general principle. There are all kinds of instruments to estimate all kinds of things from that kind of framework. They're very testable over identifying restrictions you can look at. And in fact, the statistically most efficient way to use that information is to simultaneously estimate everything, local and aggregate magnitudes, by full information maximum likelihood. Yes.
So I'm just trying to grapple here with what you're saying, the difference between volume and arithmetic.
Okay, so in our example, Saudi Arabia is a big producer of oil in the world market. So if you take a volume weighted average, Saudi Arabia counts a lot. So if you take an arithmetic average of all the producers, it's not such a big deal. And the basic idea is that difference can, in some situations, measure what's special about Saudi Arabia compared to other places.
So volume here is market share.
Production. Yeah, the quantity of the total. We're going to be looking at total stuff that happens and what's the share of any individual unit in that total.
So how does that differ from the arithmetic?
It's just an average. To get an average, I take Saudi Arabia's 1/nth plus US is 1/nth. And whereas if you're going by quantity, Saudi Arabia is much bigger.
So it's the difference between treating everybody equally,
yes,
and weighting them by their shares.
Yes.
Okay.
That's the idea of granular IV. So the contribution of our paper is to point out that there's a rich set of things you can exploit in that kind of framework, show how to do it, how to estimate with maximum likelihood, and then we'll be using as an illustration an analysis of the world oil market. And what I want to do is actually describe everything specifically in terms of that particular data set and what we're going to do with it. So here's the data we're going to be talking about. It's monthly data going back to 1973. One thing I should mention, there's some wild things happened in the oil market with COVID. The price of a futures contract in oil actually went negative. Wild things happen in all kinds of data sets, particularly so in this data set. The variety of things people have come up with for what do you do about that. Actually, in my book I'm working on, I have a chapter on reviewing some of those. But I think one of the things people may end up doing is just dropping the COVID observations from the sample, just like we were used to dropping World War II from data sets. Anyway, that's what we're going to do. So it's a monthly data set going through essentially the present, but not using the COVID observation. So the basic observation, QIT, is going to be the year-over-year growth rate in production of crude oil from country I as of month T. And a key magnitude we're going to be looking at is how important is producer I in the world total, summarized by this number SQI. So SQI is going to be a big number, for example, for Saudi Arabia. And by taking the volume-weighted average of all production, we get total world production of crude oil. Now, in the empirical example, we're just going to concentrate on the three biggest producers of oil, which are the US, Saudi Arabia, and Russia. We put all other global production into the fourth category so that the sum of these four producers by construction equals total world. So we're doing this, we're going to illustrate this in the context of small scale VAR, for which you have to have some other tools you get into if you want to have a much larger number of individual units. And one could do that. I think the right way to do that is probably with Bayesian methods. Christiane and I have a bunch of papers on Bayesian stuff, and we wanted to write one that wasn't Bayesian. And actually, I like maximum likelihood because it's very concrete. It's exactly, okay, here's the assumption, here's how instruments work. You can test it all over identifying restrictions. So this is how we're going to do our example. And then analogously, we've got CJT, which is the growth of consumption of oil in country J over as of month T. SCJ is the share of J in global oil consumption. And our empirical analysis is going to use the three biggest consumers, which are the US, Japan, Europe, plus the rest of the world, will be the fourth category. Now, it's not the case in our data set that total world production of oil equals total world consumption of oil. In fact, it's not the case in anybody's data set. And there are a number of reasons why those numbers aren't the same. One is because of measurement error. The production data is assembled from different sources. From the consumption data, they're never going to add up to the same number because of that. Another issue is there's some conceptual differences in that production is how much oil comes out of the ground, and consumption is how much ends up going to consumers. And there's a difference between those. For example, biofuels are a source of fuel for consumers that didn't come out of the ground. There's a refinery process gain because to make the crude oil, you use some natural gas. And in the process of that, you actually create more than a barrel of product from a barrel of crude oil. And finally, there's inventories. Production could be less than total consumption if you ran down your inventories a bit. So our model is going to take all three of those features into account. The measurement error, the conceptual difference, and inventories. So here's the basic model we're using to think about this. There's a supply curve for country I. This is a structural model. That there's a short-run response to price and short-run elasticity of supply given by this parameter phi qi, and finding out what that number is a key object of interest. And then there are lots of lags. So xt minus 1 is going to include the previous year's data on all the variables we're talking to, which are production of every individual country in the world, the four, as we categorize it, the consumption of every country, and the price, the real price of crude oil. So we're allowing all of those in an unrestricted way to enter into the supply coming out of country I in period T. And so that is, we have enough lags that we can treat these error terms, UQ plus U chi, as serially uncorrelated. Anything that's predictable about the country I supply, by definition, we're going to include in these lagged structural parameters. Now, I'm distinguishing in the error term there between UQ, which we'll call a supply shock, and U chi, which we'll call a measurement error. How are we going to be able to distinguish between those two? Well, our basic assumption here is that measurement error is not going to matter for the world price of oil, whereas production does. And so we'll be using the correlation between what happens in country I and the world total to distinguish between measurement error and a true shock to production. So we're defining use of QIT as the production from country I in period T, the true production that you couldn't have predicted based on the past, based on the dynamics, and it's not a response to the price.
So in other contexts, we worry about supply decisions being forward-looking, thinking about expectations of prices, what other countries might be doing. Is that?
Yeah, well, so we're not going to be doing that, except, so there is the, you'd have to put that into this setting. So this is an old style supply curve in that sense.
So on the measurement error, is that potentially correlated in country across time? I mean, you would think that if this were a reporting issue, that some countries included the distillate from natural gas in the output and others didn't.
Yeah, so there's going to be a constant term. So actually the first element of X is a constant term. So we can put anything that's fixed over time in that.
It wouldn't be a fixed quantity, it would be a fixed fraction.
Well, so this is in growth rates. So so if it's fixed quantity, it's different out with growth rates.
Yeah, right.
So, but again, by construction, this thing is not predictable.
Okay.
We've got a constant term, we've got lags.
Yeah.
That thing is not predictable.
Okay.
Okay, and there's an analogous demand curve for country J. There's a short run elasticity of demand, phi CJ. Some structural dynamics that incorporate anything predictable in any of this stuff, and then a true shock to demand for country J, and possible measurement error in the consumption data we have for country J. And as I said, true production doesn't have to equal true consumption because of inventories. So we're going to have a latent inventory demand equation. We're not going to observe this directly. We're going to get some information about it from the difference between consumption and production. And inventory demand also will allow to have a potential respond to price. It may be if there's a temporarily high price, people sell out of inventories, and that would correspond to a negative value for this parameter phi V. So inventories are imputed from the difference between total true production, which we get by taking measured production for I, subtracting off this measurement error, weighting it by the share of country I and adding up. Total true production minus total true consumption is inferred to be inventories, and inventory demand is assumed to have this structure. Okay, so putting all that together, here's the structural model. We got a series of supply equations. There's an elasticity, short-run elasticity of supply, phi QI, for country I, to respond to the price. Stack those, if you like, into a set of n equations for the n different producing countries. We have another stack of m equations for the consumption, observed consumption growth in all of the different countries. And then there's an equilibrium condition. So we're taking the view that it's a world market for oil, which I think is very much the correct view for this particular product. It's essentially the same price people pay for the oil anywhere in the world, and that's determined from supply equals demand, which demand basically including the inventory equation. So that's what that equilibrium condition looks like in terms of the implication of price of all this stuff that's going on from producers and consumers, along with the potential action of inventories.
Okay.
Yeah.
Can I ask a question on the settings? So if I were to apply this on textile industry, for instance, which is a more dynamic industry where the market shares change by way more.
Okay, so we have dynamics in these xt-1, so all kinds of, but those are constant dynamics over time. We are going to be treating the shares as fixed over time. That's part of our approach. And one challenge with doing that more generally is if you used observed shares, time varying, those would include these things we think are measurement errors, and also have some other features that we're not quite sure how to model. So we can do, and we have done, you can break it into sub-periods and look at different sub-periods. That would be the way we would adapt our approach to that general question. But we're basically taking these shares, we're using average shares over the full sample. Okay, so we've got n plus m plus 1 observations for every month. We've got production for each of the producers. We've got consumption for each of the consumers. We've got the price, world price. We're interpreting those as evolving over time as a response to these structural shocks to supply, structural shocks to demand, structural shock to inventory demand, and potential measurement error, as far as we've got to observe variables that aren't the same as the truth. So how can you estimate these structural parameters like demand elasticity, supply elasticity from these observed data? Well, you can do that if you make certain assumptions about how these structural shocks are correlated. And what I want to do now is talk through various examples of assumptions you might make. First is, how do you motivate granular instrumental variables in this setting? So let's take a special case of that framework I just described. Suppose all countries have the same demand elasticity. So it's the same parameter phi c for every country. And suppose that the demand shock for country J has an idiosyncratic component and a component that's in common with all of the other consumers. So there's like a global shock to demand and a country-specific shock to demand. And suppose that global shock to demand is showing up the same way in each country. So then this term U sub C JT, this thing I was calling a shock to country J's demand, is the sum of two components: a global component, which is going to be common to every country, FCT, and a purely idiosyncratic. Okay, so then I've just rewritten my demand equation with that assumed structure to the demand shock. Now, suppose you take an arithmetic average of that across countries, by which I mean you take each country, multiply by 1 over m, and add the countries. That's what I mean by arithmetic average. So on the left side, you're going to get an average consumption growth. The right-hand side is the same phi c for every country, so you get that same term back when you take an average of it, phi c times pt. You get some new coefficients that are multiplying the lags, which are an average of the coefficients for each country. If it's the same FCT for every country, you get that FCT back when you average across countries. And then you get this thing that's like an average of the idiosyncratic shocks to consumption and an average of the measurement errors. Okay, so let me just put those two equations again together. You've got the demand curve for country J. You've got the arithmetic average. Suppose I take the difference between those two. Difference between what happens in country J and what's happening to the average country. So it's going to cancel out the role of price. That's key because that was one of the endogenous things here. It's going to give me some new coefficients on the lags, difference between those vectors we had. And but the same FCT, so that's going to difference out. I can get rid of the aggregate factor in demand by taking the difference between this country's observed consumption and the average country's consumption. And then I got something left that's a function of these purely idiosyncratic shocks. Now, if the idiosyncratic shocks to demand are uncorrelated with the shocks to producers, if supply shocks are different from the idiosyncratic component of demand shocks, then I can use that difference between country J's consumption and average consumption as a valid instrument for estimating any supply curve. Now, it's not necessarily that great an instrument because the idiosyncratic shock to one country's demand doesn't have a very big effect on price. It's a valid instrument, just not going to be very good unless country J is really big. Even then, it's probably not that great an instrument. But we can get a more powerful instrument if we sum those valid instruments across countries, weighting the countries more that matter more for global consumption. So suppose I take now a share-weighted average of consumption. So in the arithmetic average, Europe is not such a big deal, Japan. Let me take Japan, better example. The arithmetic average Japan is not such a big. Arithmetic average Japan is a big deal. In the volume average, it's not such a big deal. So then that difference between volume-weighted average consumption and arithmetic average consumption is going to be a valid instrument for estimating supply elasticities. Yes.
Is there some sort of parallel here bringing year fixed effects in some of these equations? I mean, just looking at it.
There are no fixed effects. This is purely a forecasting equation. But no year fixed effects.
But it sounds like CJT minus C bar T are differencing some sort of a fixed element of. It just looks like what would happen if these things if you were to put it. It sounds like you put
That's true. That's right. It's like the variable people throw in when they do that.
It sounds like there's some analogy to a year fixed effect and using that as an instrument. I don't know.
So in general,
Just from an interpretation.
I'm not as enthusiastic about year fixed effects as some people are, because you're taking all kinds of stuff that A, wasn't predictable the year before, and B, is often totally related to everything you're interested in. Like what happened to global oil markets this year? That's the question in this paper. But that's an interesting observation. I should think about it more. Yeah, Mark.
If your countries are about the same size, you don't have any instruments.
There wouldn't be anything here.
And is that useful for providing some more intuition on what the variation is?
Yeah, well, so Gabay anyway is real big on this whole granular idea. That he really pushed the idea, well, there's somebody that's really big, and that's what we're really exploiting here. As you'll see, when we get to it, we're using some different features, but certainly for this particular one, yeah, it's pretty critical that those are different.
I mean, and maybe this is, you're going there, but the weighting in principle, you could choose any weighting instruments, right?
That's right. That was the point I made, that once you go through this algebra, you realize there are all kinds of things you could do here. This is just one. And in fact, you can do something more basic that doesn't require that there's this factor structure to demand at all. You can use, if it's the case that the supply shocks overall are uncorrelated with the demand shocks, that gives you a number of other potential identifying restrictions. In particular, if I were to take the observed Q, vector of production for each country, if I somehow knew the phi C, the sorry, if I knew the VQ, the supply elasticities, and I knew the BQ, I take that function of data. It should be uncorrelated with the difference between C and phi C times P. There exists a vector phi Q and phi C that would give me supply and demand shocks. And if those guys are uncorrelated, that observed thing should be uncorrelated. Any elements of that matrix should be zero in the data. So in practice, what would you do? Well, you can take the residual from an OLS regression, for example, of QIT on XT minus 1. That's observable. You take OLS residual of CJT on same stuff. That's observable. And you can imagine for what value of phi QI and phi CJ would I get something whose sample moment is approximately zero? Yes, Richard.
It seems like actually with the oil markets, the converse is the interesting question, which is, does OPEC plus in changing its supply exploit demand shocks? And
Okay,
that seems testable in this framework.
yeah, I think you could represent that as a particular concept of what phi Q is for those guys, right?
Possibly, yeah,
You're going to respond to price.
right.
We haven't worked out the algebra for that, so I don't know.
But
it's related to Johannes' question.
Yeah, anyway, it does seem like there are all these strategic interactions with the oil producers and whatever, which,
Yeah, we're looking at a framework where we can summarize those with an elasticity, short run
Right.
elasticity. Now, so if m equals n equals 1, you just got one equation here. And you can't estimate the supply and demand elasticities. This is the standard example of supply and demand from every textbook. You just got one observed thing, a correlation between quantity and price. You can't separately identify a supply elasticity and demand elasticity from that one correlation. But once you start to look at individuals, you've got a correlation between Saudi production and price, between US consumption and price. Those are lots more things. And there's potentially information here to now estimate elasticities from those cross correlations. Now, furthermore, once m and n are bigger than 2, you've got over-identifying restrictions. There aren't going to be any values that make that exactly 0. You can test that, and actually in our data, you reject it. So that implication of granular instrumental variables is inconsistent with our data set. Turns out that would not be a valid instrument because you can test this implication. And so what we're going to be using is a framework that's more general than any of those assumptions I talked about so far, that is consistent with anything we can test in the data. So we're going to allow these true supply shocks to be correlated with the true demand shocks. But we're going to restrict how they can be correlated, assuming there's just a single global factor, call it FT, that accounts for those correlations. So our specification is a little generalization, what we had with the granular IV. This vector of this vector of true demand shocks is some vector times a scalar, this global factor that's going to affect both supply and demand, and another vector times a factor that's just specific to consumption demand. So this bit is a generalization of what we had before. We were saying to use granular IV, all the countries had to have the same loading on the factor, demand factor. We're going to estimate something where each country can respond differently to this global demand shock. And then there's a true idiosyncratic component, eta CT, which is unrelated to both this condition affecting both supply and demand shocks and unrelated to the global condition affecting demand.
So for the second term, it seems like a good explanation for that is that because countries are spending so much of their foreign currency reserves on oil, that, in other words, if you had if countries were in a different import-export sort of situation, you would get exactly the second.
All right,
The countries responding differently.
in effect, operating through the price is going to be incorporated in our definition of fee C. If when the price goes up, you have fewer reserves to do stuff, so that's why you buy less oil. That's our definition, our concept of fee C.
Okay.
The short run demand elasticity. No, we're thinking of it instead, I guess, related to what Prashant was saying, sort of like a global recession. Going to bring demand, everybody's demand down.
Yeah, so what are the country-specific effects then?
Well, something might have happened in that country where different from other countries, and they were buying more or less oil than others. People, you don't think there would be such thing?
Well, no, I was just trying to actually think of good stories to.
What is it?
Yes,
Um,
because that's just a story that it is something. That was my advanced.
Well, so
story.
the U.S. economy might do better than other countries, for example. There's a global boom, but we're really doing well.
Oh, okay.
For reasons unrelated to
Oil.
oil and unrelated to other countries' temporary strength. Okay, so that's a structural model. Associated with the structural model, there's a reduced form, which is just a plain vanilla VAR. I'm going to take each of these 9 variables, regress it on a constant and 12 lags of all the 9 variables to get an equation for forecasting. Forecasting, for example, U.S. oil consumption as a function of lagged U.S. oil consumption, lagged European oil consumption, lags of prices, all lags in this equation. That's the VAR. And the VAR estimates of pi hat and the variance covariance matrix of epsilon represent sufficient statistics for the data if everything has a Gaussian distribution. In other words, those numbers from estimating VAR would summarize everything that could be known from observing all this data. And so you could use that as a framework for talking about, okay, how good a summary do we have of the data from our particular structural model? So the relation between those errors you'd make predicting these variables and these things that we're calling structural shocks is summarized by this set of equations. So if you took the error forecasting each of your productions minus these supply elasticities times the error you make predicting world price, that would have a weighting on this global factor, FT, a potential weighting on a separate world supply factor, FQT, a purely idiosyncratic shock to demand, and potential measurement error. So we're saying that error you make predicting this thing is a combination of those structural things. And likewise for the others. And then the observed price is an implication of the equilibrium condition for the world oil market, with all these shocks to supply and demand potentially influencing price, as well as a potential shock to inventory demand. The production doesn't have to exactly equal price in each period. So that's the basic structure model. So we're going to assume that these pure idiosyncratic shocks are uncorrelated with each other. So there's some variance covariance matrix if you took just the idiosyncratic shocks, and it's diagonal. Idiosyncratic shock to country 1 is uncorrelated with that for country 2. We're going to normalize the factors to have unit variance and be uncorrelated with each other. This factor FT that affects everything is by construction uncorrelated with this factor just changing world consumption. And we're going to also simplify make it more parsimonious by supposing that these measurement errors have a common variance. There's some parameter sigma squared chi, which is the variance of any country's measurement error in production. And
Is that a plausible assumption?
um,
I mean, if you assume that this is differential reporting systems,
yeah, you might well want to generalize that.
I mean, you could think that there's a group of countries that are sort of good at reporting.
Yeah, we could do something like that. So in our application, we've got kind of probably good guys at reporting.
Yeah, you've got good guys and you've got
And maybe
you might
another
you might
data
actually
set.
have three groups. You've got good guys,
Yeah.
liars, and sort of marginally competent bureaucracies.
Yeah, so we looked at various specifications. Again, the key thing of this is we're going to test this. So
Right.
we're going to test it all as one big,
Yep.
Buy the package or don't. And we did this partly because we're not as interested in those guys as
Right.
any others. But you could do
Yeah, the
various
question
things.
is, does it make a difference?
Yeah, I don't think it's going to make a difference. But
Okay. But it's also, it is an interesting test because there's a lot of concern about how good the reporting is, and you would think Japan and Europe and the US and
Yeah.
whatever are good, and you would think that Russia is bad.
yeah. Okay. So here's the implied variance covariance matrix for stuff once you subtract off the right supply and demand elasticity. So there's a structure to it. So this, for example, the 2-1 block there, it's a 4x4 block of equations. That's the correlation between the supply shocks and the demand shocks. In those first two examples I talked about, that was assumed to be all zeros. We find it's not all zeros, but we model it as a rank 1 matrix because there's a single factor FT that's accounting for those correlations. So that's then you can see that the measurement error, for example, the sigma squared chi, shows up in your observed output equations, but is assumed to have no impact on the price equation, the last row there. We got these diagonal sigma q's. So that's the basic set, which is restricted. It's a restriction on what the variance covariance matrix of these 9 forecast errors could look like. And we test those restrictions and we find they're not rejected. So that's the basic approach. So let me show you what we find. So here are the maximum likely estimates of the elasticities, along with their standard errors, which we're going to calculate by taking second derivatives of the log likelihood function, usual way. And so these supply elasticities, short-run supply elasticities, are all estimated to be small and positive. By the way, there's nothing in our approach that enforces them to be positive. It's kind of pleasant that they all came out to be positive. They all came out to be small, which is the conventional understanding. Okay, the short-run response of supply to price is pretty small. The one difference is Saudi Arabia seems to actually be responding in a significant way to the price. And so people have looked at these with obviously very different methods from ours, but that's again a fairly common consensus that people think Saudi Arabia is first able to respond to price and does respond to price.
I mean, it is interesting. I mean, that's the conventional wisdom that this would pop out that strong.
Yeah. And so there are estimates like that, but they're using very, very different methods to get something similar. And for demand elasticities,
So on split, do the other countries all tend to just run closer to capacity, whereas Saudi Arabia is actually kind of
so Saudi Arabia, literally has this lever they can turn to change the flow on a monthly basis.
So actually, when I teach economics, I show people the production from these different countries, and it's basically smooth except for Saudi Arabia, who has He seems responsive in different ways. So anyway, this is,
Yeah, so that's fine. And the demand elasticity is a little bit bigger in absolute value, but still small. And again, that's kind of consistent with what people think. Now, there's an implied global supply elasticity, which is the volume weighted average of those individual numbers. That turns out to be 0.06. Again, sort of typical number people might use. So these numbers are not shocking to anybody, but this is the first time anybody has tried to simultaneously estimate individual demand elasticities, individual supply elasticities, use them to reconcile a global phenomena. That's original with us, but we're coming up with answers similar to what people expected, I think.
I don't know if it's possible, but can one split the inventory demand in Saudi Arabia specifically and one of the other countries? Because it seems part of the story.
So yeah, there's nothing in our framework that forces the I's to be the same as the J's. What we did in our strategy was use the biggest producers and the biggest consumers. In the case of the US, it's on both lists. But in the case of Saudi, yeah, they're going to be on the supply list and not the demand list. So and it's really just, you could put Saudi consumption in here. That we could do. If you wanted to add one or two more variables, we could certainly handle that. For that matter, there's no reason, you don't have to have n be the same number as m. It's a general framework it's going to use. It was really in the interest of parsimony that we made this decision. Let's take the three biggest producers, the three biggest consumers.
A year seems like short run on supply. On demand, you could make a case for you're actually allowing some adjustment, like to public transit or something.
Yeah, there are more things you can do. Yeah,
Right?
it's in terms of the physical process.
Yeah, a year is long enough to change some.
Well, no, this is
week or
monthly.
month.
This is monthly.
Oh, this is not monthly.
Yeah.
Oh, okay, so that's
It's year-over-year growth, but it's monthly data and we've got lag, so it's
Okay,
a very short run response.
Sure. Okay. And the Europe coefficient, of course, is there's more public transit there, so they can argue that.
Yeah,
So they
yeah.
can switch more easily when the price goes.
Lexi?
Yeah. So the fact that the Saudi supply coefficient and inventory demand coefficients have similar magnitude, can we interpret that Saudi Arabia is doing nearly optimal thing? Because I think adjusting inventory is very easy. And so if the numbers are very similar.
Well, so optimality gets into Richard's question of are they being strategic? It's certainly the case that those two numbers, inventory demand and Saudi supply elasticity, are the key stabilizing factors. If you have a shock, as you'll see in the examples, that's really a key thing that Saudi Arabia is going to increase production when we need it, and people are going to sell out of inventories. I didn't comment on this. So this is a negative number, fairly significant. And that's important. There's some people that claim, well, inventories are destabilizing. When the price goes up, people accumulate even more. It's some kind of hoarding thing. And that would be a positive value fee. We get a strong negative value, that a temporary increase in price is met to a fair degree through sales out of inventories.
The way this is measured doesn't actually use any inventory data, right? Did I understand that correctly?
What's that?
The way the inventory piece is measured is using the discrepancy between.
Yeah, we're not measuring it at all.
Yeah.
Our data are production, consumption, and price. And so this is imputed from the fact that we see some stuff happening to production, which given these low elasticities would mean a really big move in price. We don't see, we certainly see some change in price, but not that big. And the way you reconcile it is with this. Okay, and then there are loadings on the global demand factor. So this is normalized a little differently from what we had in the granular instrumental variables idea. So that one, so here the factor has standard deviation 1. So these are coefficients like 2, but they're fairly similar. So in fact, that wouldn't be that bad an approximation of this data if you want to say there's some global factor and it's to some degree moving everybody the same, though it's to the extent there's a difference. We're talking about US, Japan, Europe demand being driven by a common thing, and the rest of the world by that common thing, but less so. Okay, so the last thing I want to do is go through some examples of how you could use this framework. Yes, Richard.
Before we go on, one of the things in this model, like you could obviously add more countries
Mhm.
systematically. You could like separate out China, which is
But let me just say this about China.
Yeah.
Of course, we wanted to put in China. When we looked at the data, we found it's very problematic. If you look at Chinese oil consumption
more
numbers,
production probably.
well, consumption is where you really want it because
Right.
it has become very big in the world.
Yes.
But we don't talk about this in the paper. But anyway, so
Anyway, this wasn't really a question about China.
yeah, I know.
So does this model get more efficient or less efficient as you de-aggregate the rest of the world?
In principle, more disaggregated is better. The one issue is we're setting up in this VAR, so we're estimating, we're including the lags of all the variables in every
Right.
equation. And if you added, many more variables, you'd really need to do all that stuff. And there are things you can do. There are well-known approaches to that. And we were at one point thinking of that kind of application. The other issue is that the data don't go back that far. We actually had to go through monthly issues of Monthly Energy Review to get these supply numbers going back to 1973.
But if they don't exist at the country level, then
You could do
So-
some other kind of aggregate like OPEC or whatever. Yeah.
yeah. I mean, because a different sort of strategy here would be to say, disaggregate, put all the South American countries and the African countries and whatever
Yeah.
in here, which wouldn't dramatically increase the.
Yeah, we could do things like that. I think in general, what we were thinking of was a system with a whole bunch
Right.
of countries. And actually we played with that a little bit, but we decided these other issues, how you're gonna
Right.
make it parsimonious were a little distracting. There's the argument, one paper should have one idea.
Yeah, I was gonna say, I don't know if you should do it here. I just wondered if in general.
Yeah,
things
for
that are
sure,
better.
for sure, that's like one of the next steps.
Right, okay.
But something you have to handle with that is the whole question of parsimony. You gotta
Right.
have something in common. We, as I say, like the Bayesian way to do that. But anyway, we haven't done it. Okay, so a couple of quick examples. One is what happens if there's a one standard deviation increase in global demand. So this thing that causes every country to have higher oil consumption this period than you would have predicted based on stuff in months before. So on impact, that's going to change consumption by this. So we're talking about something that simultaneously raises US consumption by 1.4%, Japanese by 1.5%, and so on. We've got a model of the whole oil market, so we can tell you from our parameters, okay, that means in equilibrium, the price of oil is going to go up by 2.3% when this happens. And furthermore, there are going to be responses of each individual supplier to that price increase. And here's a table summarizing what those are. So first column is this direct effect, not thinking about general equilibrium feedbacks. There's a direct effect that US consumption goes up by 1.4% and so on. No direct effect on production, the price goes up by 2.3. But then there's an elasticity. The US is going to increase production slightly in response to the increase in price, and that's what's given in this second column. There's also a demand response, so we basically shifted the demand curve, but then when the price went up, you're going to move along the demand curve. And each country is going to move along their individual demand curve, and so here's the magnitude of that effect. And here's actually what happens. In equilibrium, consumption doesn't go up by as much as the demand curve shifted. Now, these are all in percent of that country. There's the units are the growth rate in that country. If you're interested in the world, we multiply each of those by the share in the world total. So you can see what we basically have is like a 0.15% increase in total world production. And that's largely coming from Saudi Arabia, because they're the ones that are responding within the month to the shock. And a bigger part of the adjustment comes from consumption. Consumption is choked off by this demand surge. So you got a 0.15% increase in quantity supplied. You have a 0.9% decrease in quantity demanded. Those two don't sum to the 1.4% approximate change in demand. So what's the difference? The difference is inventories. So as I was saying, that's a key stabilizing factor. So it's a dynamic model. We can tell you not just what the effect on impact, but what's the effect 2 months later, 3 months later, and so on. And this is summarizing those dynamic questions for how each of our 9 observed variables would react over time in response to this shock to demand, world demand for oil. And so, for example, the last 4, you see this is kind of a temporary shock in terms of the nature of the structure. Consumption is higher for a few months and then goes back to where it was. So it's a temporary shock. Saudi production, so it increases on impact, it's going to increase even more if you give it a couple of months. And that's there. The price is going to rise. It's going to be a little bit higher in the second month than on impact.
Sorry. So in your analysis, did you include like seasonal times? Because it seems like there's a lot of cycles.
No, one of the reasons we took this year-over-year growth was to control for seasonality.
Oh, it's year-to-year growth.
Year-over-year growth monthly.
I see.
And
So
so
you're comparing like December of last year and December of this year.
that's correct.
Oh, I see.
Yeah, so I don't know about the Saudi thing. It has that sawtooth. It's not quite, so these are months. I'm just going out to 1 year here. I don't think we estimate things reliably, the effect 2 years down the road. Okay, yes, Fred?
Jim, am I right in this stabilizing role of inventories that you mentioned? Am I right in thinking that the coefficient that you showed us before that was larger to minus 0.31, I think, is inversely related to the coefficients on demands, for example, because of the
It's inversely related to the size of the price response.
yeah.
The bigger that number in absolute value, the smaller the price is going to change because the more of that added demand has been met with inventory sales.
So the question is, you mentioned that you've tried several periods, several time periods. Is it the case that for shorter time periods, or just getting to the 70s, to the 80s, to the 90s, where we have a lot of oil shocks, that number is smaller, so market got more efficient?
I'm not sure. I don't know if I looked at that. That's an interesting question. We should look into that. But I want to briefly give a second example, which is what would happen if there's a 50% cut in Russian oil production, obviously motivated a little by the current news. So that would correspond, I'm going to give these numbers in terms of million barrels a day, which is how they're often reported. So we're talking about roughly a 5 million barrel a day shortfall in global production. Now, as we were just mentioning, historically, inventory adjustment has been a big part of the response. It's not going to work for this example. We're going to have run through all our inventories and the Strategic Petroleum Reserve pretty quickly if we try to deal with this out of inventories. So we're actually going to run our model with the counterfactual simulation. Inventories can't change. I'm going to force all of the adjustment of the world to take the form of either produce more or consume less. And we're going to use our model to find out what happens. So here's the answers for those cases. So on impact, we're talking about a 50% drop in Russian production, which if there's no stabilizing effect of inventories means the price goes up by 31%. The responses of price to that, and then a net effect. So we actually allow Russia to increase yeah, partly in response to its own increase in price. I don't know if you want to do that. It's not very important. And then a net effect. And we summarize the net effect here in million barrels a day. So you can see in this case, by construction, when all is said and done, production has only gone down by 3.8 million barrels a day. Why? Well, again, Saudi Arabia has been pretty important. They stepped in for almost 1 million barrels a day of that shortfall. But again, the demand responses are, the biggest factor. And then we've got dynamic responses as well. So that's a little flavor of what you can do with this, what we do with it. And let me stop there, see if there are any other questions. Yeah.
That you set out making a comparison to the granular instrumental variables. And I was hoping you could just elaborate on how what you ended up doing next with that. Is the maximum likelihood essentially taking the optimal at this point, or?
So you can actually describe the first order conditions for maximum likelihood as instruments, using particular instruments. And we know from the fact that full information maximum likelihood is asymptotically efficient, that's the optimal way to use everything. The real, the thought process was when we kind of engaged a little bit in the discussion of here, well, couldn't you use this also or that also? Why do you do this? And that's what made us really want to say, okay, let's use the single principle here, maximum likelihood, one-stop shop answer to all those questions. Yeah, does that answer your question? Okay.
Okay, thank you.